Yeah, welcome to this session. So in this session, I will actually talk more about how people are using Analytic Zoom to build real-world big data AI applications for their end-to-end solution or pipeline. So this is a recap of Analytic Zoom. As I mentioned before, Analytic Zoom is built on top of those low-level frameworks or libraries, and provides the end-to-end pipeline for users to seamlessly scale their AI models to distribute big data, as well as high-level machine learning workflows to automate a lot of those tasks. In practice, we see our users are building different types of applications on top of Analytic Zoom. Those applications can be roughly categorized into 4 categories: recommendation, time series analysis, as well as computer vision and natural language processing. So next, I will actually show some examples and dive into the details of those cases of how those applications are built in real world. So first, let's look at some recommendation examples. First is the Burger King case. It's actually a very interesting use case. So by the way, we have a technical blog as well as a talk at the Data Plus AI Summit. So if you're interested in more detail, you can refer to that. But at a high level, as I mentioned before, we have your customers driving into your drive-through restaurant, and inside the drive-through restaurant, they have a menu bar, and it shows a bunch of items. And the customer can talk to the cashier to have the cashier to enter the order. As the cashier is actually entering the order, then we use that information to do real-time recommendations. So you can see there will be new items actually showing up in your menu board, and the user can look at those recommendations and maybe add something to their order. That's actually actually, as I mentioned before, AI is really moving everywhere, right? Even if you are selling a hamburger, actually you are trying to use AI to improve that process. So it's on the other hand, food recommendation, especially those drive-through fast food recommendation, is a bit different from those conventional recommendation on your shopping website, on your e-commerce. There are a lot of challenges, new challenges. First of all, you don't have the user identification. Unlike you're going to your Amazon or Alibaba, you basically have your user IDs, and they can put a lot of the history and the profile and to do recommendation. But in those drive-through environments, you really don't have those user IDs. And also, you need to look into the order session carefully, right? It's unlikely that you are going to order 4 different drinks, for instance. You just order 4 different drinks in one order session. It's very unlikely. And also there are a lot of other, I would say, context information. What are the location? What are the weather? What is the time? It's unlikely you're ordering some tried food at midnight. It's very unlikely, and so on. So there is a lot of different challenges you need to deal with in this fast food recommendation scenario. So what we end up doing with Burger King, essentially, first of all, build a new model. We call it a transformer class transformer. Basically, it has 2 components. One is you use one transformer architecture to look at the item ordering sequence. Right? As you add item into your order, we take that as a sequence and using a transformer to extract features. And then there is a bunch of context information, like as mentioned, the location, where the time, and so on. We use another transformer architecture to extract those features from those contexts. And then we do a so-called latent class between those context information and the sequence information for joint prediction.
Hey, Jason, what's the storage architecture that's behind this solution? I mean, this is happening at the restaurant, or is happening in the cloud?
Well, the training is happening in the cloud.
The training's happening in the cloud. Okay.
Yeah, the training is definitely happening in the cloud.
Through like a Hadoop cluster or something like that, or?
Yeah, I have this page.
Okay.
So yeah, I just talk about the model, and then the next of the mention, you need to do a end-to-end data processing and model training. And there is, I mean, again, there is two approaches. The conventional approach, really, you have a Spark cluster running on Yarn. You do a bunch of data processing. You need to process a huge amount of transaction data. And then you store it on a distributed file system, and then you use another cluster. In this case, you're using MXNet to do the training. That's one way to do that, more of a conventional way. But as I mentioned before, there is a lot of challenge in terms of data movement and end-to-end development and so on. That's that's it. At the end, what we end up doing is that we try to run the entire end-to-end data processing and model training on a one unified Yarn cluster, and using Spark to do data processing, using Ray on Spark. I mentioned a little bit, using Ray on Spark to provision your MXNet training, and inside the Yarn cluster, we can directly feed the Spark in-memory data into a Ray cluster for distributed training.
So Jason, can you maybe talk about the use case for a second? Because I'm trying to put this in context. Okay. You know, when it's the recommendation is happening in real time, right?
Yes.
Okay, and it's happening at the menu board as opposed to in an app or through some other means.
Well, in this drive-through case, right? It's happening in your drive-through restaurant. You have outdoor display menu board. And it's happening in that place.
So my question is, what are the data inputs, right? Because I do eat Impossible Burgers at Burger King, and I do use their app. So I'm trying to figure out, like, what are, you know?
Well, it's essentially
what's the inputs?
Yeah, the two inputs, right? Actually, if you look at the model, there are two inputs. One is your order sequence. So as you add item into your shopping basket, kind of, so you take your order sequence as one input. The other input is really the kind of context. What are the location? What is the time? What is the weather? And so on.
And so is what happens. I order my Impossible Burger, and I order a Diet Dr. Pepper, and then as I order that and it gets put in by the person, then does the board change in front of me?
Yeah, the change. And as you order, when you first arrive at the restaurant, this is the board. Uh-huh. And as you order it will add items which is doing the recommendation for you.
So it's not truly personalized. It's just based on what I happen to be ordering, and then all those other variables, like is it breakfast?
Yeah.
Okay. Gotcha.
Well, and it's probably also. I'm also guessing
it's very. Sorry, go ahead.
Go ahead.
No, I'm just talking. As I mentioned, I mean, in a drive-through environment, it's impossible to get the user ID, so it cannot get all those history information and so on. So it's based on that ordering information and other.
Yeah, I was going to say, you know, if I order a burger and I order a soda, it's going to recommend that I have fries too, because I didn't order fries. So it's going to find those common.
Yeah, try to do that. One example that. Yeah, one example that if you order a bunch of orders in the beginning, they kind of know it's a heavy party type of context, and they can do something. Yeah, basically look at the pattern of the history ordering.
It's going to be onion rings at Burger King, not fries.
I mean, where it would be really interesting is if you were like Gina and you actually used the app and it recognized that Gina was in the drive-through, and Gina tends to order these pieces, these components, that it would actually suggest, hey, do you want to order this again?
Or maybe they would give me free onion rings, and that would be even better. Because I'm so loyal.
Yeah, I think that's actually, as I mentioned, that's an interesting use case, right? AI is really moving everywhere. I mean, it's no longer on your shopping website, on your auto drive. It's actually going to everywhere people try to use it to improve their efficiency. So this is the result showing that offline results showing the accuracy, prediction accuracy with different models, and also they are doing A/B testing here to see the improved conversion. I mean, they are based on some improved conversion rate and add-on sales gain, right? So likely you are going to take their recommendation and what are the additional sales they can get through this recommendation.
In this kind of use case, so what is the format for storing the big data?
Well, basically the big data is stored in, the input data is really the transactional history, right? They look at all the history of the transactions. Those are stored in the Parquet file and the Hive data warehouse. They are basically distributed file system. Yeah, so if you're interested, there is we have a technical blog at the Rice Lab website. We have a talk at the Data Plus AI conference. We also have a paper, technical paper. I may not show it here. We have a technical paper as well. I showed previously and talk about the technical details. So if you're interested, you can always refer to those details. So next, I will just talk very briefly in this use case because this is also a recommendation use case. But essentially, Mastercard has you might not be aware, but they're running a bunch of recommendation applications inside Mastercard, and they have their looking at their transaction data, which is stored in their Hive data warehouse, running on their Hadoop cluster, actually in this case Cloudera cluster, and where they need to run many different recommendation models for different applications, and they are using both Midea and Analytic Xeon to support the TensorFlow models and so on. So that's actually another example of how people are using Analytic Xeon to build those recommendations. For instance, one example is the how likely you are going to do shopping in this this merchant so that they can push an offering to you. This type of applications actually they are running intensively in their big data class as well. So we talk about the recommendation use cases. Next, we'll look at some of the time series analysis. Actually, time series analysis is also widely used in different industries, whether it's manufacturing, maybe it's telco, 5G networks, in financial industries, and so on. So let's look at the SK Telecom use case. So as mentioned before, SK Telecom is the largest telecom company in South Korea. So this is a map of the city Seoul. So every dot in that map, the green dot and the blue dot is a base station. Is that base station, and the color shows how healthy that base station is. And you can see there are some warnings if there is a network quality related to that base station. So what SK Telecom trying to do here is that they collect the network quality indicators. There are a bunch of indicators from their base stations. They collect it every few seconds or minutes, and they get all those network quality KPIs and try to predict what are the network quality will be for anomaly detection and the real-time management.
So with this, are they bringing in outside data as part of that to build those models, or is it just strictly based off of internal data?
Yeah, it's strictly based on their internal KPI data generated by their network device in their base stations. As you can see, a bunch of indicators, channel quality indicator, what are the signal to reference noise ratio, so a bunch of many KPI data in their base stations. And they have history, right? You have a KPI every few seconds or every few minutes. You have a long history data. And actually, if you look at this model, it gives a better idea what they do, right? They try to they look at the last 15 minutes data and try to predict the next 5 minutes what the KPI will look like. But in addition to the last 15 minutes, they actually use a memory network. So basically, what it looks like in the same time period over the last 7 days, I take that and use attention to build essentially a memory network and then I use my last 50 minutes plus those history data to predict what the KPI will look like in the next 5 minutes. And this shows one example of essentially they are showing two different models. You could using a sequence-to-sequence model to do the sequence generation, and they have, as mentioned, they built a memory network. As you can see, the blue, the yellow ones are essentially the ground truth, and the green ones are the prediction result. And you basically plot those time series data on a chart, and you can compare the ground truth and the prediction, and the memory network actually improve the prediction for sudden changes a lot. I mean, you can actually more accurately predict if there is a sudden change in your network. And then, essentially, as I mentioned before, they have a lot, really a lot. I think more than 400,000 base stations, and then they need to get their KPI data. Each base station generates a ton of KPI data, and they need to stream their KPI data into their big data system. I think it's about 1.4 million records per second. They need to stream into their data, their KPI data into their big data system. They have built a Redis and LockDB based big data storage, and after you stream those KPI data into their systems, they use Spark SQL to query the data and analyze the data. So next, as I mentioned before, after they analyze the data, they really want to build a model, a prediction model. In this case, is a memory network to predict what the KPI will be in the next 5 minutes. So they start with a kind of, I would say, legacy design. It's a kind of conventional. You export your data from your Spark cluster into a CSV files. You ship it to a GPU server. You process it you process the data in pandas or Dask, and then you're doing AI training or inference using TensorFlow on the GPU server. So they start with that, and they see a lot of overhead. You could imagine that shipping the data between the clusters have a lot of overhead. But also, more importantly, they have new data coming in almost every second, every minute, and they need to update their model or maybe apply their model to the new data. So the end-to-end development cycle becomes very, I would say, awkward in this separate architecture, separate cluster. So that's why they are moving to Analytic Zoo to provide a unified data analytics and AI platform. So you can do all the data pre-processing on Spark and then transform that into a RDD of tensors, everything in memory, and take a TensorFlow model and run it on your Spark cluster for distributed training and inference. Well, this one shows example. This is the inference example. On the inference side, you can see, well, first of all, on a single node, you can get about 3x speed up, 2 to 3x speed up. And then when compared to running separate clusters on GPU, and then the other part is Analytics, as mentioned before, it takes your code and without any change, it can seamlessly scale that out across a cluster. So you can get even more speed up by seamlessly scaling out. This is for training. This is for inference, and this page is for training. As you can see, on the training side, on a single node, you actually get competitive or comparable performance with your GPU training. But again, we seamlessly scale that out. You can get up to 4x speed up when we scale out to 3 Xeon servers. So this shows you actually by running your AI models, integrating into your end-to-end data pipeline using Analytic Zoo, it actually improve both the end-to-end performance or speed as well as your development productivity.
The advantage here is the traditional solution is running on a single server versus the scale-out capabilities of Analytic Zoo. Is that how I'm reading this?
There are three bars, as you can see. The first bar is it's a single GPU. And the second bar is essentially a single Xeon server. And the third one is essentially scale out on 3 Xeon servers. So you see more details on this white paper, but roughly speaking, on a single Xeon server, you can get about the same performance as a single GPU, but you can simply scale out.
How much work is involved to go from a single server to a cluster of servers or multiple?
Yeah, in analytics use case, it's as I mentioned before, it's almost a zero code change. I mean, it's essentially the analytics unit as a platform to try to automate that process. It will automatically partition data and replicate the model and perform a data parallel training or inference. So everything is transparent to the user. So that's the goal we have in analytics unit. Basically, provide
So I write the code once, and whether it's on a single system or single CPU or multiple, Analytic Zoo will handle that for me.
Yeah, I mean, I think you just need to change one line of the code to specify what are the cluster, what are the number of nodes that you're going to use, and then use a command to submit that to a Yarn cluster or Kubernetes cluster. Yes. Mm-hmm. So I talk about SK Telecom, how they use time series to analyze their network, their cell towers. The next example is actually another interesting example. I think it's GoldWind is actually a large, I would say, wind power manufacturer as well as operation company, and we all know that wind power is a clean power. We all like it, but it's important to predict what are the power you're going to generate from a wind power farm, because the nature of wind is not very reliable. Right? Sometimes you have a lot of wind, sometimes you have very little wind. But it's important from a power grid point of view. You can predict how many power you will generate from your wind farm. So that's actually the problem try to solve using time series analysis. Basically, as you can see here, you collect all those information from your wind tower, the tower of the wind power generator, and then you real-time data is streaming into your system, and then you process the data again using Analytics Zoo and the TensorFlow to do distributed training, and then you can, in this case, we're using LSTnet to do distributed training, and then to use history data as well as a lot of the information about the weather, about the power generator and so on, to do the prediction. It actually improves your accuracy a lot, as well as improve your training speed a lot. So that's another example of how time series analysis is used in real world. We actually use distributed TensorFlow on Analytics Zoo to allow users to actually scale that out.
How does Analytics Zoo enable more accurate prediction?
I think it's the accurate prediction is, of course, because we have for two reasons. Right? First of all, you have a good model, and then you need to look at a lot of data. So the model side, of course, it's a conventional TensorFlow model. You can build it in TensorFlow, and then you need to deal with those huge amount of data. So analytics allows you to first directly apply the model to your production data and seamlessly scale that out so that you can process more data and analyze more data and with the automatic scale out.
So effectively, what you're saying is you're training with more data with the Analytics Zoo solution rather than the traditional solution.
It allows you to basically train with all the data you have, and you can essentially distribute it across a cluster. I mean, you can run it in a large amount of servers, and which allows you to train with more data. Yes.
Well, okay. I guess maybe is that the reason why? Because it's easier to do the training across a larger population of systems, then you're more apt to use more data. Because if you were confined or constrained by resources, you might choose to only use a subset of data or smaller data sets because of the computing resources.
I think there are two primary reasons. First of all, when you try to apply AI or deep learning to your production environment, you need to essentially have an architecture at least compatible, ideally integrated into your production data pipeline. And in those cases, a lot, as I mentioned, again and again, we see in Mastercard, we see in Burger King, and so on. They have data managed by their big data system, Hive data warehouse, package files. We have people running in Elasticsearch and so on. You really need to bring those AI models into a big data system. Otherwise, you end up doing a lot of data copy, data shipping across the clusters. So that's one of the reasons it's become more efficient. I would say in a way, it's lower the barrier for people to bring AI into their big data production environment. And secondly, as I mentioned before, it takes advantage of the big data cluster. It makes it much easier for users to seamlessly scale out to run distributed training and inference, and allows people to train with more data or with faster speed and so on. Next, we'll look at some computer vision examples. What people are doing using the computer vision again in some interesting use cases. This is actually one example of in Midea and KUKA, who basically they have a lot of manufacturing pipeline with electronic appliance like air conditioner, microwave, and so on. As those products are coming off their pipeline, they need to manually inspect the product to see if there are any defects. So they end up what they're trying to do here. They're using industrial robotics, attach a camera into the robotics, and I'm not sure if you can see this video, but essentially it can take a picture of this product, and then after you take the picture, they basically are using object detection. As you can see here, there is in this picture there's supposed to be 3 bolts, but they only see 2 in that picture. So there is a missing bolt, and they can use computer vision to do the product defect inspection, so that you can see whether there is a defect in the product. So in this case, again, they are using a TensorFlow object detection model, but they have a bunch of images, a lot of images stored in the distributed file system. So we use Spark to do the data processing, and again, take the TensorFlow model to the distributed training and the distributed inference or evaluation. And the interesting part is that it's not only running on a cloud, right? It's not on a server. You do the training on your Spark cluster, but then when you try to do the prediction, you really need to do it on the edge. In this case, they are just running a bunch of Java web servers on your on Intel Core processors at the edge to do real-time inference or prediction. They have it shows very good result in terms of accuracy, as well as the speed up in terms of image processing and the model inference. Well, another example is actually it's more or less similar to the case in that it's essentially Dell EMC is building a prototype which takes your chest X-rays and using transfer learning. And I think people mentioned this problem, right? You don't have actually a lot of labeled chest X-rays. So what they end up doing is using transfer learning with the image with the ResNet pre-trained with the ImageNet, and take your chest X-rays and essentially to do the prediction of what are the disease you can detect from this chest X-ray. So that's again an example of how people are using computer vision on top of Analytic Azure for their use cases applications.
Is this the GE Healthcare example?
No, it's from Dell. It's from Dell. They actually have a kind of prototype taking those X-ray to build a prototype. So finally, in the last section, I want to talk about some of the natural language processing use cases people are building on top of Analytic Xeon. This is an example of Microsoft Azure. They actually have built a kind of a cast service chatbot. So you go to their UI, you can have a web UI or a UI on your phone. You can basically input some questions to say, how can I get my invoice? Or how can I shut down my VM and so on. So with those natural language based question input into their UI, what they are trying to do is that they will go to their internal knowledge base or their Q&A documents and try to find the right answer, right document and return to the user. They start with a keyword search algorithm based system. So basically take your question and using keyword search and to retrieve the document. And in order to improve the accuracy or relevance of the answer, basically they take Analytic Xeon, especially there are several built-in models inside Analytic Xeon, for instance, to do the QA ranking. So basically with the question and the answer, I will try to rank how relevant they are. And based on that ranking, they will return the top relevant answer to the user. And then after the user gets that answer, they may or may not be happy with the answer. So if they are not happy with the answer, what they want to do is they want to connect to an expert, to a real person who can answer a question. This is actually a very costly behavior, a costly operation, because you need to assign a real expert to answer the question. So it's important that you can accurately route the request to the right expert, right? If it's an invoice problem, you want to route it to a financial person. If it's a VM problem, you want to route to a technical person. So basically, they use a text classification model, try to classify the intent of the question. And based on the intent, they can accurately route the question to the right expert to provide the answer to the customer. So yeah, there is more information. We have 2 technical blogs published. So as you can see here, there's more information, more technical details in that. But essentially, this is a very interesting example of how people using the NLP capabilities building on top of some of the built-in models provided by Analytic Xeon to provide this customer service chatbot. Well, this is the last example I want to show in this session today. Essentially, this is a kind of a job search, a job recommendation example. Essentially, in Talroo, there is a lot of documents, right? They have the resume of their customers, as well as a bunch of job descriptions. And what you want to do is really, you want to essentially when the user is searching for a job, you really want to recommend what are the relevant job to the user. And basically, the way they are doing that, of course, a lot of those documents are stored in the big data distributed file system. And then you use a bunch of feature extractions to tokenize those documents and so on. And then they run a k-means clustering, essentially cluster those users, I would say, into different clusters. And inside each cluster, you will run a neural network model to basically to build the probability of how likely that user will be applying to that job. And based on that, they can actually recommend the relevant job to the user as the user searches through their website and so on. So that's actually a good example of how you can use NLP to do this type of processing and on top of Analytic. So in summary, as I mentioned before, we do see big data AI is an important transformation the industry is going through. I think that's it's joined by two forces, right? On one hand, those big data users, big data applications are increasingly trying to build a model to predict, using machine learning deep learning to build models to predict the future and to make decisions. On the other hand, those AI algorithms, the AI researchers are increasingly moving their AI models into production. I mean, almost everywhere from selling burger to managing your manufacturing pipeline and so on. So it's critical that for the user to apply their AI to their big data platform. So to recap, there are two challenges. First of all, in your production data environment, the data is managed by your production big data system, the big data pipeline. You have Kafka, you have Elasticsearch, you have Parquet, and you have Hive and Spark and everything to analyze the data. How you can directly apply your AI models into your big data pipeline, big data platform. And secondly, how you can seamlessly, transparently scale out that big data and AI pipelines across a cluster to process a large amount of data. That's what Analytics do try to support by providing open source software platform with both end-to-end pipeline as well as the advanced AI workflow.
Hey, Jason. I guess I'm not as much as a production kind of AI user as most, but is it typical that it seems like Analytic Zoo is predominantly used in big data solutions or big data environments? I guess I'm not sure whether like speech recognition and those sorts of things would necessarily come in as a big data solution kind of at the start. It seems like, yeah, there's plenty of applicability, I guess, for the solution in Hadoop or Kafka or those sorts of environments, which are sort of big data by definition. But I don't see it for a more generic AI kind of space. Now, I understand the distributed inferencing capabilities are very unique and very useful, but I'm just trying to understand, where does this fit in an AI training environment? And maybe Frederick, you could comment a little bit more on the speech kind of stuff.
Right. I think my observation is that overall end-to-end is very important, right? And I think Jason mentioned it a couple of times. The big issue is that a lot of people try to do something on a laptop, but how do you bring that to production and at scale, right? That's a big issue. Certainly because there's a tendency for people to start in a public cloud, but then they're being railed in by saying, hey, you have to go to production on premises where you're being, you have to kind of change your model. The other thing which I think is also very important is that it seems to lower the barrier to entry to AI, right? A couple of years ago, and again, maybe for Jason, my background is speech recognition. So I've been doing speech recognition, AI, and HPC because there was no AI 20 years ago for a long time. We had to build everything ourselves, right? So if you didn't have a PhD, there was a non-starter. Data was also an issue. Nowadays, there's a lot more data. People understand what data can do for you. People are sharing data, which wasn't happening 10 years ago because people were hugging data as opposed to sharing, which is quite interesting that the opposite is happening today. But that's how I look at it. And I also want to kind of say that big data is a relative term, right? So big data, a few terabytes 10 years ago was considered big data. Today, it's just data. So I also want to make sure that we understand that big data is kind of a relative term.
Yeah, it's almost, at least at a leadership level, big data has kind of gotten to a point where it's almost a taboo thing to talk about because big data has become the big data swamp. There were all these great things that were supposed to come out of it, and that didn't materialize. But I agree with Frederick that it's now data, but there are these natural constraints that come around resources and access to resources. And so that's why I think something like Analytic Zoo becomes really interesting, especially being able to scale so easily, now it kind of opens up the art of the possible of bringing in other data sources that you might not have otherwise thought of as part of your architecture.
Right, and maybe one final point is that transfer learning is also a massive addition, right? It means that the time to results at scale is significantly reduced. I mean, 10, 15 years ago, if you wanted to build a speech recognition engine, you were gone for at least 6, 7, 8 years. Today, you can use transfer learning with an open source speech recognition engine and build some very interesting things with very little data, but relying on transfer learning. And again, the tool chain is really important, and you have to have something that's end to end. If it's not end to end, it just ends up being a project. I mean, I don't know if it was yesterday or today somebody was talking about, you know, the amount of time spent on data and the failure rate of AI projects. That is the ability going from, hey, it runs on my laptop to, you know, I can deploy that across all you know, food restaurants or whatever your application is.
But you have to take it a step further, Frederick, and that is you can deploy it into production, but it actually has to show value too. There has to be value with it. It can't just be a science experiment that happened on your laptop. You were able to move it to production and then wipe your hands clean and you're done. That's where things really start, because at that point, then it's, okay, is it really turning value?
Right, but like with anything else, I look at this as a tool. It's like having a compiler. The compiler is not going to generate great applications, right? But the tool by itself, combined with the ID and the data, will get you somewhere.
Yeah, but wouldn't you say that this is kind of taking it from, I've got to do it all myself and kind of piece together these pieces to, I mean, Analytic Zoo seems like a framework that I can leverage, take off the shelf and plug into much more easily than the alternatives.
Right, and that's what I meant with lowering the barrier to entry, right? So you don't have to super glue all the different pieces together, and people are really lucky today. I mean, they can use something like this to get something started with AI. A few years ago, you had to build your own algorithms, which was not an easy thing to do, right? I mean, today it's all being shared. It's quite the opposite, right? So when we started with speech recognition, the source code was considered the IP, and the data was just to be used to test the outcome of our program with source code. It didn't take long where we flipped it, where we actually didn't care where the source code was coming from, or at least if we had built it ourselves, it was all about the data. And we realized that because when we were trying to build a speech recognition engine, our competitors came to us and said, "We don't want your source code. We just want to buy your data. We want to license your data. It's not even buying. We want to license it."
I think, you know, we had an earlier session that talked about, you know, implementing scalability through the use of containers and those sorts of environments. And I didn't see anything in the Analytic Zoo that talked about containerization or anything like that. Is there something there?
Yeah, it's actually orthogonal. I think container is actually more about how you orchestrate your class, right? For instance, a lot of our users running Analytic Zoo on Kubernetes in production, so they are using container to deploy and to orchestrate their cluster. Analytic Zoo is actually more on, I would say, on a higher level in that how I actually connect those data together. I mean, with your container, for instance, you can still run your separate framework using container and exchange data through the distributed file system and everything, and you still need to have the code. Even container is about the deployment, how you provision and deploy. But how do you do that? I mean, analytics is at a higher level, try to solve that data and the data pipeline and the analytics AI pipeline problem. But yeah, we have a lot of users running analytics in container and running on, say, Kubernetes and so on.
Okay, thanks.
Yeah, I kind of had a similar question, but I just assumed that was the case, that, you know, when you talk about containers and Kubernetes, that's more the deployment method underlying, that what you're talking about sits above that, rides above it.
Yes. Yeah, and to add to the point, I think, well, there is no one size fits all, but But Analytic Zoo and especially so big data is really, I think, critical for people to productionize their AI application or projects, right? I mean, that's a lot of problems they need to solve when they really want to go into production environment, rather than running on your laptop and your lab environment. And that's also we see big data. Well, big data, you really the next key challenge of big data, really how you create a value. And we see today people increasingly try to apply machine learning and deep learning onto their big data so that they can build prediction and modeling prediction, and so that they can make decisions and so on, so that they can extract value from their big data. That's why we see there is increasingly demand for something like Analytics to apply AI to their big data environment.
How much of, when you think of the Analytics Zoo framework, can you characterize how people are tending to use it today? Like, what are some of the swim lanes? I mean, you talked about the 4 of them in that one chart, right?
Yeah.
But are there, if I kind of take it above that a bit, are there certain swim lanes that you're finding that people are having the most success with this, or scenarios that are kind of drawing them to Analytics Zoo?
I think the roughly there are 3 key drivers of the say people are using Analytics. First of all is, I think for big data users and the big data engineers, essentially, how they want to apply AI onto their production big data environment. That's actually one key driver. Secondary is the distributed capability, right? Distributed training and inference. How you can easily, maybe transparently scale out to a large cluster and perform large scale distributed training and inference. And the third one is a lot of those advanced capability like AutoML, like time series analysis. And those capabilities we built into Analytics Zoo, which help users to automate a lot of those tasks. There is another key reason a lot of people are trying to use Analytics.
Thanks, Jason. A very nice presentation, and I really love the exchange what you guys has had. As if you were telling for me the story that I was trying to tell you from the beginning. Remember, I talked about compute democratization, and I think quickly through that exchange, I'm realizing that we have AI democratization journey here. We're doing that, so to make it easier, accessible to everyone, to be applying AI in real production and on general purpose compute architecture, which will also reduce the TCO for customers. So I think in summary, what we covered today, we talked about the industry inflection point fueling the growth of data from 5G network to AI to intelligent edge to the cloud. And we talked about, of course, AI analytics being pervasive. And, we see that for the next decade. And we see that growing trend and demand for the end-to-end AI pipeline that Jason talked about. And I want to remind you, Intel is transformed, is becoming data-centric infrastructure to provide an unmatched portfolio to serve that intelligence era, right? From silicon to software and anything in between, we're trying to help customers to deliver those diverse range of use cases. And as you learned today in detail, that Analytics Zoo, that an open source, again, I emphasize that, not a product, for commercial. It's an open source software platform open to everyone to help address the big data AI and simplify. We do end-to-end solution.